Hi, my name is Will Summers, and this is Lab 4, where we'll discuss oscillations of a mass connected to a spring. The purpose of this lab is to track the motion of a mass attached to a spring and describe its relation to the energy principle. The energy principle, in this case, is the delta E equals the change in kinetic times the change in potential energy. By observing this motion and tracking it and putting it into a Python file and creating a model for it, we'll see that the delta E is equal to 0 and that it actually fits the energy principle. Here are the few equations that we'll use mostly. As we see first, we have Newton's second law, which is force equals mass times acceleration. Another version, V final equals V initial plus the F net over m times delta T. Likewise, we also have our energy principle, which is the main concept of this lab, which delta E equals delta K, which is kinetic energy, plus delta U, which is potential energy. Now we'll go ahead and take a look at our tracker video. As we see, we have all of our axes correct with the positive x on the right, positive y up, and we also have our distance of 0.7 meters of the spring to the mass. Here on the right side, we could see a graph of the oscillations over time, and we also have a chart that marks the x and y positions of the mass over time. I'll go ahead and pull up the tracker file for you to watch. Again, we start from an initial position and have a zero velocity, and over time you can see as the oscillations go, they're being graphed to the right and charted also on the right in the table. Okay, now we'll go ahead and put our basic information into the code. We'll start with our constants. We have a mass, which is 0.402 grams, our position, which is roughly negative 0.1, negative 0.60 meters, our velocity, which is 0 meter per second, our gravity constant, which is 9.8 meters per second squared. We also have our kinetic and potential energy equations. Our first equation for kinetic energy is 1/2 times the ball mass times the magnitude of the velocity squared. Our equation for gravitational potential energy is the ball mass times gravity times the ball position, the y. And our spring potential energy, which is 1/2 times ks, which is spring constant, times the distance squared. Now we'll go further into the spring equations. We know that the force of gravity is equal to the force of the spring based on Newton's second law. So we'll break that down, and we eventually find out that the relaxed length of the spring is equal to 0.123 meters. Likewise, for finding our k value, we know that the period was found by averaging the oscillations over time of the y's. So we'll take the equation for the period, t equals 2 pi times the square root of m over k, and we'll solve for our k, which is come out to be 6.83 newtons. For the while loop of our Python coding section, we first included our forces. We know that F net equals F of the spring plus F of gravity, and we know that the values for F of gravity would be the negative ball mass times gravity, and we know that the equation for our spring constant would be k times our k value times the s, which is the distance, times the L half value. Now for our velocity and positions, we just take what we found, or what we have for Newton's second law. Ball velocity equals ball velocity times F net over m times delta t, along with ball position equals the ball position plus ball velocity times delta t. And finally, for our energy changes, we know that we have our kinetic energies as well as the two potential energies, but this describes the change over time, so we'll have our finals minus initial. Moving on, we'll describe our motion of the balls in our Python model. So for our first model, once it'll run, here we go. We see, just looking at the computational model for this one, a red ball representing the values given to us and the blue ball representing the computer program. This is what our final output looks like. We see that the red ball is just ahead, slightly ahead of the blue, but that might be from mapping difficulties or other small forces. And going on from there, we'll go ahead and take a look at the energies that are graphed. The yellow line in the middle on the zero axis represents our total energy. And this is exactly what we want, as we explained earlier, as the delta E is equal to delta K plus delta U. And those are zero because of the total energy. The system is zero because our system includes the spring, the ball mass, and the Earth. There's no acting on the surroundings. These other lines, the green line is the gravitational potential, and the red line is the spring potential, as long as the kinetic energy, which is blue. Those all cancel out and give us our total energy again, which is the yellow, which fits the energy principle and what we want. The next part of the experiment was confirming our model versus our experimental data, as you see in that graph there. I would go ahead and run the model for a second part, which compares the two. And you can see in the graph here, they start off very well, looking pretty close. But over time, they start to separate just a bit. And that could be from, outside forces such as drag or anything else acting on the surroundings or human error during the tracker positioning. Finally, we'll ask ourselves the questions for what if and what does it mean. First off, for your model, is the energy principle satisfied? Well, as we saw in the graphs, that the total energy was equal to zero. This is true because the gravitational potential energy and the spring potential energy, along with the kinetic energy, canceled out. Second question is asking that using the tracker model, would the x position periods of oscillation and y position periods be different? Well, once I computed them, I got a period for the y to be 1.56 meters and the period for the x to be 1.77 meters. They are different values, and you would expect this because they are on different axes. And that is all. Thank you for watching.